NENOMATICA, where mathematics meets YouTube excellence. Welcome! In this lesson, we master quadratic inequalities in one variable using an intuitive sign chart method. First, we move everything to one side to get a standard form. The leading coefficient must be non-zero. Visually, the inequality p of x less than or equal to 0 means the graph sits on or below the x-axis. For this upward opening parabola, the function is below 0 between the two x-intercepts. That is exactly the solution to p of x less than or equal to 0. In this example, we'll solve the quadratic inequality x squared minus 7x plus 10 is greater than or equal to 0. We'll follow the sign chart method step by step, exactly as shown in a standard sign table solution. First, let's write the problem. Step 1. Factor to find the critical points. We treat the inequality as an equality x squared minus 7x plus 10 equals 0. It factors as left parenthesis x minus 5 right parenthesis times left parenthesis x minus 2 right parenthesis equals 0. So the roots or critical points are x equals 2 and x equals 5. Step 2. Build a sign chart. We'll test the signs of x minus 5 and x minus 2 across the intervals split by the critical points 2 and 5. Negative infinity to 2, 2 to 5, and 5 to positive infinity. Fill the row for x minus 5, negative to the left of 5, 0 at 5, and positive to the right. Fill the row for x minus 2, negative to the left of 2, 0 at 2, and positive to the right. The product p equals left parenthesis x minus 5 right parenthesis times left parenthesis x minus 2 right parenthesis is positive when both signs match 0 at 2 and 5 and negative in between. To make the solution even more intuitive, the inequality is satisfied where the product is positive or 0. That gives the solution set, negative infinity to 2 inclusive, union 5 to positive infinity inclusive. We will solve a quadratic inequality x squared greater than or equal to 25, following a clear, structured, step-by-step method. First, we show the word example, then the problem in bold orange. Step 1. Rewrite the inequality in standard form. We use the rule ax squared plus bx plus c is greater than or equal to 0. Move 25 to the left, so we get x squared minus 25 is greater than or equal to 0. We highlight the changed part, negative 25. Step 2. Find the roots of the corresponding equation. We use the equation ax squared plus bx plus c equals 0, and the difference of squares formula, a squared minus b squared equals a minus b times a plus b. So x squared minus 25 equals 0 factors into left parenthesis x minus 5 right parenthesis left parenthesis x plus 5 right parenthesis equals 0. Therefore, x equals 5, or x equals negative 5. These are the critical points. Step 3. Create a sign chart. We test intervals determined by the critical points. We place a number line, mark negative 5 and 5, and show the signs of x minus 5, x plus 5, and their product x squared minus 25 in each interval. For x less than negative 5, both factors are negative, product positive. Between negative 5 and 5, the factors have opposite signs, product negative. For x greater than 5, both factors are positive, product positive. Step 4. Determine the solution set in interval notation. We include the roots because we have greater than or equal to. The solution is the union of negative infinity to negative 5 inclusive and 5 to positive infinity inclusive. In this example, we will solve the quadratic inequality, negative, open parenthesis, x minus 1, close parenthesis, open parenthesis, x minus 3, close parenthesis, is greater than or equal to 0. Step 1. We simplify the inequality by multiplying both sides by negative 1. Remember, multiplying or dividing an inequality by a negative number reverses the inequality sign. So it becomes, open parenthesis, x minus 1, close parenthesis, open parenthesis, x minus 3, close parenthesis, is less than or equal to 0. Step 2. Find the critical points by setting each factor equal to 0. Set x minus 1 equal to 0, which gives x equals 1. Set x minus 3 equal to 0, which gives x equals 3. These values split the number line into test intervals. Step 3. We create a sign table to determine where the product is negative or 0. We consider the intervals from -infinity to 1, the point 1, from 1 to 3, the point 3, and from 3 to positive infinity. For x minus 1, the signs across these are negative, 0, positive, positive, positive. For x minus 3, the signs are negative, 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 0, positive. The product is positive, 0, negative, 0, positive. We want less than or equal to 0, so that means the product is negative or 0. Step 4. Because we want less than or equal to 0, we include the interval where the product is negative and also the zeros at 1 and 3. So the solution set is the closed interval from 1 to 3. Recap. We reversed the inequality by multiplying by -1. We found the critical points at x equals 1 and x equals 3. The sign table showed the product is negative between 1 and 3 and 0 at the endpoints. Therefore, the solution set is the closed interval from 1 to 3. In this lesson, we will solve a quadratic inequality in one variable step by step and build an intuitive picture along the way. First, here is our example and the problem statement. Step 1. Rearrange the inequality. Move all terms to one side to get standard form. The rule is bring everything to one side so that one side is 0. Starting with x squared less than or equal to a squared, we subtract a squared from both sides to get x squared minus a squared less than or equal to 0. Step 2. Find the roots of the corresponding equation. Our tool here is the difference of squares identity. Factor x squared minus a squared as left parenthesis x minus a right parenthesis times left parenthesis x plus a right parenthesis. Set it equal to 0 to find the critical points x equals a or x equals negative a. Step 3. Sign analysis. Because the coefficient of x squared is positive, the parabola opens upward. Between the roots, the expression is non-positive, and outside the roots, it is positive. We will make a quick sign table to see plus, 0, minus, 0, plus across the intervals. Let us also visualize the parabola y equals x squared minus a squared for intuition. Step 4. Determine the solution set. We want where x squared minus a squared is less than or equal to 0. Include the interval between the roots, and include the endpoints because of the equal sign. Therefore, negative a is less than or equal to x, which is less than or equal to a. The solution set is the closed interval from negative a to a. Recap. Move all terms to one side, factor to find the roots, use the sign of the upward opening parabola, and include the interval between the roots with endpoints. Your final answer is D equals the closed interval from negative a to a. In this lesson, we will solve a quadratic inequality exactly following 4 steps. First, the problem statement. Then we factor. We find the roots. We study the sign on intervals. And finally, we state the solution set. Step 1. Factor the quadratic expression. We look for two numbers that multiply to positive 6 and add to negative 5. That pair is negative 2 and negative 3. Step 2. Find the roots of the corresponding equation. Set each factor to 0. X minus 2 equals 0 gives x equals 2. X minus 3 equals 0 gives x equals 3. These are the boundary points. Step 3. Use a sign chart to determine the sign of the expression. We split the real line at 2 and 3. Because the parabola opens upward, it is positive outside the roots and negative between them. We have 0 at the roots. So we get plus on the left, 0 at 2, minus between 2 and 3, 0 at 3, and plus on the right. Step 4. We want less than or equal to 0. That means include the interval where the expression is negative and also include the roots. So the solution set is the closed interval from 2 to 3. In this lesson, we will solve a quadratic inequality step by step using factoring and a sign chart. Example, solve the inequality x squared plus 21 is greater than 10x. Step 1. Rewrite in standard form and factor. Move all terms to the left side to get ax squared plus bx plus c greater than 0. Then set the corresponding equation equal to 0 to find the roots. We factor to get left parenthesis x minus 3, right parenthesis times left parenthesis x minus 7, right parenthesis equals 0. Therefore, the roots are x equals 3 and x equals 7. Step 2. Determine the sign of the quadratic expression. The roots at 3 and 7 split the real line into 3 intervals. Because the coefficient of x squared is positive, the parabola opens upward, so the expression is positive outside the roots and negative between them. We will mark the intervals on a number line and show the signs. Step 3. State the solution set. We want where the expression is greater than 0, so we take the positive regions, from negative infinity to 3 and from 7 to positive infinity. In this lesson, we will solve a quadratic inequality in one variable step by step using the sign chart method. Our example is open parenthesis x minus 1 close parenthesis squared is less than or equal to 2x times open parenthesis x minus 1 close parenthesis. Step 1. Expand and rearrange. Expand the left side and the right side. Move all terms to one side to compare with 0. Finally, multiply by -1 to get a form p of x greater than or equal to 0. Step 2. Find the critical points by solving the corresponding equation p of x equals 0. Set x squared minus 1 equal to 0. Solve to get x equals plus or minus 1. Step 3. Sign analysis on a number line. Draw a number line and mark the roots at -1 and 1. Because the parabola opens upward, the quadratic is positive outside the roots and negative between them. We need p of x greater than or equal to 0, so we take the positive regions and include the roots. Step 4. Write the solution set. Since we include the roots and take the positive regions, the solution is the union of the intervals from negative infinity to -1 closed, and from 1 closed to infinity. In this lesson, we will solve the quadratic inequality x squared minus x minus 12 is greater than or equal to 0. We'll proceed in 3 clear steps. Factor to find the roots, determine the sign of the expression on a number line, and then write the final solution set. Step 1. Treat the inequality as an equation to find the roots. We set x squared minus x minus 12 equal to 0. Now factor the quadratic. We look for 2 numbers that multiply to -12 and add to -1, -4, and +3. So the factorization is left parenthesis x plus 3 right parenthesis times left parenthesis x minus 4 right parenthesis equals 0. By the zero product property, either x plus 3 equals 0 or x minus 4 equals 0, giving x equals -3 and x equals 4. These are our critical points. Step 2. Determine where the expression is positive, negative, or 0. Since the coefficient of x squared is positive, the parabola opens upward. That means the expression is positive outside the roots and negative between the roots. Let's mark this on a sign chart. We'll place ticks at -3 and 4 and label the intervals. To build intuition, here is the parabola y equals x squared minus x minus 12. Notice it crosses the x-axis at -3 and 4, and because it opens upward, it is above the x-axis to the left of -3 and to the right of 4, and below the x-axis in between. Step 3. Write the solution set. We want where the expression is greater than or equal to 0, which includes the positive regions outside the roots and the roots themselves. Therefore, the solution set is the union of the intervals from negative infinity to -3, closed at -3, and from 4 to positive infinity, closed at 4. In this video, we will solve a quadratic inequality step by step. We will follow the exact structure, rearrange, find roots, analyze signs, and state the solution set. Here is the example x squared is less than or equal to 8x. Step 1. Rearrange to standard form. We move the term 8x to the left and set the inequality less than or equal to 0. So we get x squared minus 8x is less than or equal to 0. This is our function p of x less than or equal to 0. Step 2. Find the roots of the associated equation. We set x squared minus 8x equal to 0. Now factor an x. Set each factor to 0 to find the roots x equals 0 and x equals 8. Step 3. Analyze the sign on the number line. We use the roots 0 and 8 to split the real line into intervals. Because the leading coefficient of x squared is positive, the parabola opens upward, so the function is positive outside the roots and negative between them. Let's draw a number line with ticks at 0 and 8. We mark positive to the left of 0, negative between 0 and 8, and positive to the right of 8. Since we need p of x less than or equal to 0, we include the interval between 0 and 8, and we include the endpoints as well. Step 4. State the solution set. Because the polynomial is negative or 0 between the roots, and the inequality is less than or equal to, the solution set is the closed interval from 0 to 8. As a quick visual recap, the graph of x squared minus 8x is a parabola opening upward, crossing the x-axis at 0 and 8. The inequality less than or equal to 0 picks the part of the graph on or below the x-axis, which projects onto the interval from 0 to 8 on the number line. That completes the solution. We followed the standard method. Rearrange, find roots, analyze the sign, and write the solution set. The final answer is the closed interval from 0 to 8. Example. We will solve the quadratic inequality negative x squared plus x minus 2 is less than 0, following the exact algorithm shown. Step 1. Set the corresponding quadratic equation to 0 to find potential roots. Step 2. Calculate the discriminant delta using b squared minus 4ac. Start with delta equals b squared minus 4ac. Substitute the coefficients. The image showed 1 minus 4 equals negative 3, but that is incorrect. It should be 1 minus 8 equals negative 7. Step 3. Analyze the sign. Because delta is negative, there are no real roots. The quadratic keeps the sign of the leading coefficient, a. Since there is negative, the expression negative x squared plus x minus 2 is always negative. We can show a quick sign table reflecting this. For intuition, only a quick sketch. A downward opening parabola with no x-intercepts lies below the x-axis everywhere. Step 4. State the solution set. Since the expression is always negative, the inequality is true for all real numbers. Recap. We followed the algorithm exactly. Set the equation to 0, computed the discriminant, analyzed the sign using delta and the leading coefficient, and concluded all real numbers satisfy the inequality. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.